Hello, my name is Hassan Murtagi. I'm a course assistant for the Data Models and Decisions class, and I'm going to be giving a tutorial on how to solve optimization problems with Gurobi and Python. Okay, so the advantage of using Gurobi and Python is that you don't have to specify the problem in dense matrix format. So what is dense matrix format? If we have the optimization problem as follows: maximize C transpose X subject to AX less than or equal to B and X is greater than or equal to 0. In some softwares like R, for example, when using R and Gurobi, you have to give Gurobi the problem in dense matrix format. So you have to provide the A matrix, the right-hand side as a vector, the vector B, and then the objective coefficients. And this is not really efficient nor helpful when you're trying to solve large-scale optimization problems like network problems, for example, that have a lot of arcs and nodes, because it's very hard to specify this matrix manually. And the advantage of using Python is that you don't have to do that. You can write constraints using loops or even manually in a very efficient way. So today I'm going to be presenting two different ways using Gurobi. One of them is writing everything in the problem manually, like the objective function constraints manually one by one. And the other way, I'm going to be using loops to show you a more automated way to solving the optimization problem. Okay, so the example we're going to consider in this tutorial is a multi-period inventory problem, and you've seen a similar problem to it in one of the quizzes. And in this case, we have 5 periods. In each period, we need to produce a certain amount to meet a demand, but we can also carry over some period and have it in inventory for the next period. So if you, as you see in this image here, in each period, these are the production costs. These are the production costs in each period. And then the numbers next to them are the production capacities. These are the upper bound on the capacity that we can produce in each period. So what's shown in blue is the inventory costs and capacities as well, respectively. And the demands are shown in red. So what are the decision variables in this problem? The decision variables are xi for I equals 1 to 5. And these are the amount that we produce in each period. And we also have ikl for k in 0 to 6 and L for 1 to 6. Sorry, this is 5. And the xi are the amount we produce in each period, and the ikl is the amount we carry in inventory from period k to period L. So notice here that it started from 0 and ended at 6, even though we have 5 periods. So what I did is I added 2 new variables to the model. And for I01, I added this variable. It's not important. I'm actually going to set it to 0 later on. But it really helps when you're writing the constraints using loops on Python. It makes it more structured, and you follow the same structure every time when you're writing the demand constraints. As for I56, it's important because it also helps with the structure, but it also allows the problem to have leftovers. Because it may be more optimal to produce, let's assume in period 3, you had a very low production cost, and a very high production capacity. So it may be more optimal to consume all the capacity you have and use it in later periods, even if it's more than the demand, than produce in later periods at higher costs and produce amounts that are exactly equal to the demands. And this I56, in this problem, it will most likely be 0 because we don't have high production capacities and costs. We don't have high production capacities and low costs early on. But this is the generalization of the problem, and this will work regardless of what the numbers for the production capacities and costs are. Now I'm going to move to the formulation. So to start with the objective function, our objective function is thus to minimize the total cost, and this is the inventory cost, total inventory cost plus production cost. Notice how I have 0I01 in blue and 0I56 in blue. This is because they have no cost in the problem. And I just added these variables. You could consider them as auxiliary variables to help when formulating the optimization problem, and also as a generalization for allowing the problem to have leftover inventory at the end. So let's start with the balance constraint. So these are the demand constraints. So let's consider, for example, node 2. So in node 2, you have I12 coming in, you have the demand at period 2, and you also have what you're producing at period 2, and then you have the inventory I, 2, 3. So the balance constraints say that, again, for each node, similar to network problems, what's coming in should be equal to what's coming out. So we should have x2 plus I12 is equal to I23 plus demand at period 2. And this is the constraints you see here. But the difference is you just move this to the other side with a negative sign, and these are the constraints you have that here. So this was for node 2, these are for all the nodes we have. And again, you see why I added the I01 and I56 constraints. You see them here. You see that the structure is very nice. You have the same structure for all constraints, and when writing loops later on, you'll see why this is very easy and useful to do. And then the final constraints are the production capacity constraints. You have x1 less than 40, x2 less than 100, and these are the production capacities as I previously saw. And then finally, as I previously described, you have 40 for period 1, 100 for period 2, and this is what you see here. And finally, we have the same thing for the inventory capacity constraints. As I mentioned earlier, you see that I set I01 to 0. It's not helping the problem anyway, but it just makes writing the problem on Python easier. And finally, I56, it doesn't really have an upper bound because you can have as much leftover inventory as you want. So I just put 1,000 because if you go back to the problem, you see that 1,000 is the largest production capacity out of all periods. And it's impossible that your leftover inventory will be greater than your maximum production capacity. So this is why I put 1,000. You can put 10,000. The number is not really relevant. This is just the upper bound I chose. So these are the constraints. We just have one more constraint, which is that all variables are greater than 0. So production variables xi is greater than 0, and inventory variables I, k, l is also greater than 0. This is obviously obvious because you cannot produce negative values. So now moving on to solving with Gurobi. So here is a Jupyter notebook file that I solved the problem. I solved it two different ways, as I mentioned early on. So the first way is I did everything manually, and the second way I used loops. And I'm first going to start with the manual method because it will help you understand the one that's automated using loops later on. So the first thing is from Gurobi import, you're importing the Gurobi library. And then you start by defining the optimization model. So here you see the syntax. You have m equals model. And then you call the model, you give a name for the model. So here it's the 5-period inventory problem. And the first step is you create your decision variables. So the decision variables, as we previously mentioned, is the inventory and production variables. So to start with the production variables, here's the syntax. So we have x1 is equal to m, and m is the same as what we equated to the model defined earlier. So this is syntax is m.add var is how you define variable, and your v type is Gurobi continuous. And this is the type of the variable. It could be Gurobi.integer and it could be Gurobi.binary. It depends on the problem. Here it's continuous. You give it a name. You specify a lower bound and an upper bound. In this case, the lower bound is 0 and an upper bound is Gurobi.infinity. And I'd like to let you know that the default when specifying a variable in Gurobi is that it will be continuous and it will have a lower bound of 0 and an upper bound of infinity. So we didn't actually need vtype, lb, and ub in this case. I just have them here to show you that these could be changed. And the final term is the objective coefficient. And Gurobi recognizes that when you add an objective coefficient, it knows that this is going to be the sum product of the coefficient, objective coefficient, with the actual variable in an objective. It knows that this is going to be a linear expression that has a coefficient multiplied by the respective variable. So, and then we move on to the inventory variables. We have the same thing. So we start from I01 and end to I56. It's the exact same thing. We have a continuous variable with a lower bound of 0 and an upper bound of infinity. But note that here I have an objective of 0 for I01 and an objective of 0 for I56. And the objective of 0 we have for I45 is because the problem, this is the numbers of the problem. It was 0 in this case. So after you define the variables, the syntax of Gurobi is as follows. You must update. You must have this m.update because it integrates the new variables into the model. So the next step is the constraints. So we have the production capacity constraint. We just have m again, dot, the syntax is dot add constraint. And here you have x1 less than 40, x2 less than 100, etc. And these are the names of the constraint. You don't need to actually give them names. It's fine if you don't. But note that actually we could have eliminated these capacity constraints completely. We could have, instead of having the upper bound as Gurobi infinity, we could have put these upper bounds. Like we could have put 40 for x1 here, 100 for x2 here, etc. The same thing applies to the inventory capacity constraints. Notice here that I have an equality constraint for I01 and I set it to 0. And here are just the inventory capacity constraints we have defined in the problem. And for I56, I gave it an upper bound of 1,000 as I previously mentioned. So moving on to the final component of the constraints, the balance constraint, very easy to do. You have m.add constraint, I01 plus x1 minus I12 is equal to 10. And then you have the same structure. What's coming in is equal to what's coming out. And here again, I named them demand 1, demand 2. You don't need to have these names, but you can see here the nice structure of the constraints and how I01 and I56 are fitting into the structure and making it easier to model. And after defining all the model components, you print m. You have m.optimize, and then the model runs and it outputs the result. So a good thing to do is you print. You have a model status m.status, and Gurobi has a numerical number for different statuses. So here in the output, you see that the model status is 2. This means that the model is feasible and optimal. If you have an infeasible model, you will get a different number for that. So it's very useful to output the status. And a very powerful tool that you can do with Gurobi is you can actually write the LP. So you can say m.write linear program.lp. And if you run the model, it will save this LP file in the directory in which you're running your Python code. So if you look at this linear program, you can see that it writes the LP for you. And this is a very good way of checking that your code is right. So when you write an optimization problem and you see that it's not working or you get errors, this is very useful because it always helps you diagnose where your problem is. And if you look here at this LP, you see that it's exactly the same formulation as the one we have in the slides. So then you can move on to printing your decision variables. You say you have a loop for m again. The m is the model dot get vars. This is the syntax. And you print v.var name, this is the variable name, comma, v.x, and this is the value of the variable. So finally, we want to print the objective value, and the syntax is as follows. You have m.objective value. And you can see the output here. So you see the values for x's, which is what we produce in each period, and the inventory values we have. And you can see as expected that I56 is 0. And I01 is 0 because I set it to be that way. And these are the inventory capacities we have for each respective period. Okay, so this, you can see here that in this case, we defined everything manually. But what if we had 100 inventory period? It would be very, very tedious to define the problem manually as we previously did. And the second way I formulated this problem is using a more automated way, using loops. So first, again, we create the model. You say m.model and you give it the name. And what I did was I took the data of the problem and put into lists. So these are the production costs for each period. So 22 is for period 1, 42 is for period 2, etc. And 450 is for the last period, period 5. And the production capacities, so this is the upper bound for what you produce in period 1, upper bound what you produce in period 2, and finally the maximum that you could produce in period 5. I did the same thing for inventory costs, but now note that these were 5 values because you have 5 periods, but for inventory costs, now there's 6. And I have 0 because I added I01 and I56 to the model. So you see that inventory cost for I01 is 0, and for I56 it's also 0. And again, if we go to the inventory capacities, here, again, there are 5 values because I don't have a capacity for I01 because I'm going to set it to 0 anyways in the problem. And finally, we have the demand for each period defined as follows. So let's start by creating the production variables. So here I have a production variable and I create an empty list, okay? And then I run a loop. And it runs 5 times because it's in the range of the length of the production costs. You have 5 values there. It runs 5 times, and each time it appends a Gurobi variable to that list. So if you have 100 periods, it would just be very easy to define your production variables as follows. So here you can see we have production add variables dot append. It adds to the list each iteration. Again, it's the same syntax as we saw previously. M dot add variable. Again, you have the continuous variable. As I mentioned, it's set that way by default. You don't need it. And notice here that I removed the lower bound and upper bound because, as I mentioned, it's set default by Gurobi. You don't need to specify it if your lower bound is 0 and your upper bound is infinity. And the power of using that is that when you can say name equals x curly brackets dot format of I plus 1. And it's going to name the variables each time. So this I plus 1 is going to go and replace this curly brackets. And I have plus 1 because in Python, the loop, as you all know, it starts from 0. And I want my variable to be called x1. So in the first iteration, it's going to be called x1, and it's going to end at 4. So when you add plus 1, it's going to go from x1 to x5. And your objective is the production costs of I. And this is the list that I defined for the production cost. It's going to go and give each iteration, it's going to define the variable and give it the production cost defined in the data earlier. We do the exact same thing for inventory variables. We go in the length of inventory costs. And remember that this is a list that has 6 items. So this loop is going to run 6 times. And we do the exact same thing. In each iteration, we append to that list a continuous variable. And the name here, it has I, and then you have 2 components. So notice here that we start regularly with I because we have a variable I01 that I want to create, and I want to end at I56. So it's I, and then I plus 1. And then again, finally, we add an objective coefficient to that, which will be in the objective function. And it's the inventory costs I defined earlier. So it's gonna go, and each time we run the loop, it's gonna create a new variable, give it that cost. The next loop, create a new variable and give it the following cost, etc. So again, after we define the variables, we need to update the model to integrate the variables. M.update. This is very important. If you don't have it, you will get an error. So now we move on to the production capacity constraints. Again, notice here that I could have had an upper bound of production. I could have added here, UB is equal to production capacities of I, as you see in this part here, but I didn't do that because I wanted to show you how we could write the constraint. So again, we create a loop for the length of production cost, and then we say that the production variable, the respective production variable is less than or equal to its respective production capacity. And we do the same thing for inventory capacity constraints, but here there's a little trick, is that I have I plus 1 here because I'm starting with I12. I01, there is no capacity for it. I'm setting it to 0 anyways. So this is going to start with I12 and then move on to I23 until it reaches I56. And again, as I mentioned earlier, that we have only 5 values for the inventory capacity. So this I plus 1 will go from will go from the second inventory variable up to the last one. And then finally, we add the same constraint. We want to set I01 to 0, and this is the first inventory. This is the first variable in the list of inventory variables, which is I01, and we set it to 0. And then finally, the balance constraint. And here you see again the same structure we had previously, the very nice structure. You go in the, we're going to have 5 constraints. So we go in the length, you go in the range of the length of the production cost. It's going to run 5 times. And you say that your inventory variable of I plus your production variable in that period minus your inventory variable in the following period is equal to the demand in that period. So for example, if we're in node 2, this would be I12 plus x2 minus I23, and this would be equal to the demand value in that period. And notice that we defined the demand earlier as a list, so it will go and grab the respective values in each iteration of the loop. And this is the power of using Python. And again, we run m.optimize, and we look at the model status. You see here model status 2, and we get the exact same results when we solve it that way, and it should be that way, of course, as when we solved it using the other method. And when using loops, you can see here that the indexing is tricky. And when using loops, especially with the indexing way in Python, how loops start with 0 and end at the value you give it -1, it makes it tricky, and sometimes you can get confused with the indexing. And writing your saying m.write the linear program is very useful, because loops can be confusing and you could be missing something, especially with the hard indexing system. And you can usually get errors saying that your index is out of range. And by looking at the by writing your linear program, as I mentioned, it's very useful to diagnose your problem. So again, we say m.write linear program 1. Let's go to a linear program. You see here that it's the exact same program as the one wrote using the manual method, and of course the exact same formulation as the one we have in the slides. And then finally, we do the same thing. We print the decision variables using m.getVariables, and in each loop you print the variable name along with its optimal value. And finally, you print the objective value using the same way we discussed earlier. So this is the end of the tutorial. I hope this helps you with Gurobi and makes it clear, and also helps you understand the similar inventory problem that was in the quiz that was causing some problems and confusion. Thank you.